All right, so we're going to talk about sensitivity, specificity, positive predictive value, and negative predictive value. And this is what we're going to be working from. Here we can see the test results. So positive and negative as denoted by the test result. And then disease or no disease, which is the truth. Okay, so we have true positives. So these are people who have the disease and the test said they had the disease. We have false positives. They don't have the disease in reality, but the test said that they did. We have false negatives, those with the disease but weren't caught by the test. And then we have true negatives, which are folks who are not diseased and were also tested negative. And then we have total for the test positive, total for the test negative, total disease, total no disease, and the grand total. Okay, so let's talk about prevalence. Prevalence is the proportion of individuals in a population having a disease or characteristic. To estimate prevalence, researchers randomly select a sample from the population they want to describe. So let's think back about sampling. When we randomly select from a population, everyone in that population had an equal opportunity to be selected. Therefore, it is representative. So we're looking to see what is the proportion of individuals in a given population that have a disease that we're interested in. So for a representative sample, the prevalence is the number of people in the sample with the characteristic of interest divided by the total, the grand total. So let's look. The number of people in the sample with the characteristic divided by the total number of people in the sample. So what is this? This is A plus C. So this cell, the true positives, and the false negatives divided by the grand total. So A plus C, the total of disease, divided by the grand total, multiplied by 100. So how is prevalence different from incidence? Incidence is a measure of the number of new cases of a characteristic that develop in a population in a specified time period, whereas prevalence is the proportion of a population who have a specific characteristic in a given time period, regardless of when they first developed the characteristic. We don't use this contingency table to determine incidence. So therefore, incidence is the total number of new cases in a given time period over the population at the start of that time period. So sensitivity is the probability that a test will indicate disease among those with the disease. That's this cell here, the true positives. We want to know what's the sensitivity of a particular test, and that is this cell, those with the disease who tested positive for the disease. So we do A, which is this cell, divided by A plus C, okay, or just the total disease. So true positives divided by true positives plus false negatives times 100. So specificity is this cell, the true negatives. It's the fraction of those without the disease who will have a negative test result. And that is D, which is this cell, over D plus B or B plus D, or the total. So true negatives over true negatives plus false positives times 100. Note, sensitivity and specificity are characteristics of the test. The population does not affect the results. And as your population changes, your test doesn't change. So it is a characteristic of the test and will remain the same regardless of the population. So if you're a test developer, this is what you're interested in. You want to know what is the specificity and sensitivity of the test that I have developed. Now, if you're a clinician or a patient, you have a different question. You want to know about the truth. You want to know what is the chance that a person with a positive test actually has the disease. If the subject is in the first row in the table, what is the probability in cell A compared to cell B? A clinician calculates positive predictive value, the PPV, which is A over A plus B. So before sensitivity was interested in this column, now positive predictive value is interested in the rows. So A over A plus B, which is the total test positive. Similarly, what are the chances that the subject with the negative test really doesn't have the disease? This is the negative predictive value, which is D over D plus C times 100. So let's look at an example. We have 100 people who were tested for a disease. 15 people have it, 85 don't. So here we are. 15 people, regardless of how they test, have the disease and 85 do not. So the prevalence is this cell divided by this cell. 15 divided by 100 is 15%. So what is the sensitivity? Remember, that's the probability that a test will indicate disease among those with the disease. So that's this cell divided by the total cell, which is 67%. So our sensitivity is 67%. The test misses 33 of the people who have the disease. All right, so what is specificity? Remember, that's the fraction of those without the disease who will have a negative test result. Those are the true negatives down here. So that's 45 divided by the grand total, or the column total. So 45 divided by 45 plus 40, which is 85. And we get 53%. So in other words, 45 of these 85 people with negative results are truly negative, and these 40 test positive for a disease they do not have. But we care most about the positive predictive value and the negative predictive value. So check it out. The positive predictive value, remember, is A divided by A plus B times 100. So here we have 10 divided by 10 plus 40, so 10 divided by 50, which is 20%. So only 20% of the people who test positive actually have the disease. So 20%, is that good? Not so good. What about the negative predictive value? Remember, that's this cell, those true negatives divided by the false and the true negatives. So 45 divided by 5 plus 45, or 45 divided by 50, which is 90%. So for those that test negative, 90% do not have the disease. But we want both of these values to be high. Let's look at another example where we have the same test, so our sensitivity and specificity will not change. They're the characteristic of the test, so they remain the same at 67% and 53%. But we're going to increase our prevalence. So the number of people in the sample with the characteristic divided by the total number of people in the sample. So now we're going to go to, instead of 15, we're going to go to 30. 30 divided by 100 is now 30%. And these are our numbers. So let's calculate PPV and NPV. So the positive predictive value, that's this here, 20 divided by 20 plus 33, and we get 38%. So we've increased. We actually have capturing more of the people who actually have the disease, they're testing positive. So that makes sense. When the prevalence increases, our PPV increases as well. Well, what do you think happens to the NPV? We look at this cell, 37 divided by 10 plus 37, which is 37 divided by 47, which is now 79%. Our NPV decreases when the prevalence increases. Using the same test in a population with higher prevalence increases positive predictive value. Conversely, increased prevalence results in decreased negative predictive value. This figure depicts the relationship between disease prevalence and predictive value in a test with 95% sensitivity and 95% specificity. When considering the predictive values of diagnostic or screening tests, recognize the influence of the prevalence of the disease. So let me just ask some questions. Under what circumstance would you really want to minimize the false positives? So minimizing false positives is important when the costs or risks of follow-up therapy are high and if the disease itself is not life-threatening. For example, obstetricians must consider the potential harm from a false positive against potential benefit. So consider a maternal serum AFP test, which if positive may be followed up with amniocentesis, ultrasonography, and increased fetal surveillance, as well as producing anxiety for the parents and labeling of the unborn child. When would you want to minimize the false negatives? We don't want many false negatives if the disease is often asymptomatic and is serious, progresses quickly, and can be treated more effectively at early stages or easily spreads from one person to another. Which pandemic does this remind you of?